We continue the lecture on the economic evaluation of the process design. This is the third part of the lecture 2. So we have been looking at the fixed operation cost and the variable operation cost. Then one of the major elements in operation cost is a utility cost. So the steam is widely used in the industry in terms of providing the heat to the process. So steam is the most widely used heating medium in process industry. There are several reasons for that. So the first one is steam has a high heat of the condensation. So compared to the heating medium, the steam is powerful to carry the heat and bring the heat and transfer the heat within the process. So you will see that the example later, how we can provide the steam, how we can distribute the steam. But in the industry, we typically producing steam through the boiler. Say we have the boiler, then through the burning of the fuel in the boiler, we have the steam. So rather than direct supply of the heat, then the steam is used. So there are some place where we need some heating, then the steam will be transferred to the place where heating is needed. Then steam is used. Then the process stream get the heat from the steam. So this is a common way of providing the heat in the process industry. The other one is the process stream is directly connected or linked with this boiler. So that is called the furnace. Then the stream temperature, process temperature is increased through the burning of the fuel. So this is a direct heating. This is a kind of the indirect. The reason to use steam is sometimes this place where heating is required is far away from the source of the energy. Then also there are many different places, okay? A, B, C, and P, okay? So then we needed to provide steam in a different place. This is quite the useful way of making the steam in a central place, in a common place. Then the steam is distributed, okay? So that is the common way of providing the heat in the process industry. Sometimes this direct heating is required. So it's direct heating is more economy than this steam production and the distribution maybe economy. So in the process industry, it's a mixture of this direct one, this indirect one against this direct one, okay? Then the steam is used because of the high heat of the condensation, okay? So steam is used in like a heat exchanger, and then the heat is transferred to the process stream. And we are typically using the heat for the condensations part. So latent heat is large compared to the other one, like flue gas or hot oil or other heating medium. So these flue gas or hot oil are typically utilize the sensible heat. But steam, the heat exchange is based on mainly the latent heat that enable us to keep the large amount of the heat through the steam that will facilitate better heat transfer. So the small flow rate means in the size of the unit for the heat transfer and the heat exchanger and other heat exchanger equipment can be reduced. That is another benefit of the having smaller flow rate for the heating medium. So the steam is widely used because of the large amount of the heat of condensation or latent heat. Okay. So also the steam has the high heat transfer coefficient. Okay. So high transfer coefficient means less heat transfer area is required compared to other one. So you might remember the heat exchanger area will be governed by this simple equation. Okay. What happened for the heat exchanger area? So if U is big, then the A will be reduced. Okay. So if the U is low, then A will be increased when Q is fixed. So heat duty of the heat exchanger is fixed, and the heat transfer coefficient is reduced, and the heat exchanger area is to be increased. So the better heat transfer will be good in terms of the saving heat exchanger area. Smaller heat exchanger area means and less capital cost. Small investment on the capital cost for the heat exchanger. So high heat transfer coefficient given as here as an overall heat transfer coefficient means we have the small the investment, capital investment heat exchange area related with heat exchanger. Okay. So temperature of the heat provision can be controlled by steam pressure. Okay. So the stream condition is governed by these three things. Okay. So the pressure and the volume and the temperature. Okay. So when we want to control the certain property or the characteristic of the stream condition, we typically control either by pressure or temperature. When these two things are fixed, then the property of the steam will be determined in a unique condition, thermodynamic condition. So when you control the pressure, then temperature will be influenced by the change of the pressure because of the thermodynamic the relationship. Okay. So temperature change, then of course the pressure will be accordingly changed. But in a steam case, it might be easy to control the pressure, and it's not that difficult to change the operating condition for in terms of the pressure control. Then the temperature can be controlled accordingly. So how do we control the pressure of the steam? So there are, let's say, steam here. Then sometimes we want to reduce the pressure. Sometimes we want to increase the pressure. So how can we decrease the pressure? The one of the thing is so-called throttling valve. then we can reduce the pressure. The other one is using the expander. Then for the steam, we call the turbine. Then the pressure is reduced, okay? Then in some case, we needed to increase the pressure, then we have to use a compressor. But when we are using the steam, we are typically producing very high pressure, then reduce the pressure. That is quite common. So these two devices are commonly used to control the pressure. When we decrease the pressure either by the JT valve or the turbine, then the temperature will be accordingly determined by the pressure for the outlet, okay? So by changing the pressure throughout this device, we can control the temperature here. So the maximum temperature is limited to approximately 250, okay? So of course we can make the steam higher than more than 250. So 300, 350, but that may not be economic, okay? In terms of the heating, typically we are providing heat until 250 degrees C, maybe 280 degrees C. So that is the kind of the threshold for the maximum temperature typically allowed in the process industry when steam is used. Above this temperature, we use the fire heating, maybe hot oil, okay? So the higher temperature, for example, 400, 450, maybe 500 degrees C, then the steam is not used. Now we needed some fire heating, direct heating through the furnace. And the another thing to use steam in the process industry is related with operation and the safety. So the steam is non-toxic, non-flammable. If the steam is leaks, we can see that. So that is quite a useful property or characteristic in terms of the process operation and the process safety. Inert means you may need some additional the component in the processing, but that component is not involved in the reaction or separation. Sometimes we needed that kind of component for the sake of the operation or for the sake of the improving safety. Then the steam might be introduced into the process to the reactor, for example. Then that component must not be interact with other components exist in the process. So steam often used as inert for the process because the steam often not interfere with the reaction or is not involved in any reaction with the other component. So the steam is used as the inert to the processing in an industry. So we want to estimate the steam cost, okay? So the reason is to estimate steam cost is to determine the operation cost for the site. The major element in the operation cost is first the raw material cost and second is the energy cost. So we want to see the cost of the steam for determining the overall operation cost. So how do you estimate steam cost? The first case is the heating only. So the boiler is used, then fuel is burned, then feed water is supplied for the boiler, then we are producing steam. We might be producing the very high pressure steam and the high pressure steam or just low pressure steam depending on the user after the steam is produced. Then how can you calculate this cost for this steam? The first, we need to take into account the cost involved in purchasing of the raw material related with the boiler steam production. So first we have to buy feed water. So then feed water cost should be involved in the estimation. And the fuel cost, it might be coal, it might be natural gas, it might be oil. Then we have to buy the fuel in order to provide heat for the boiler. So fuel cost should be calculated first, then the feed water cost then should be added. Then based on these two things, then we have to check how much steam is produced by using the furnace efficiency. So here is the boiler, then water is feed water, then the fuel. Then the fuel might be used is 1 megawatt of the fuel. Then the steam is produced based on the amount of the fuel supplied to that. How much steam is produced, then we have to take into account the efficiency. So say if we take the efficiency is 80%, then the 0.8 megawatt will be used for the production of the steam. Okay, so the 20% will be loss. Okay, so the efficiency should be taken into account. Then what about the distribution efficiency? Then steam is produced. So let's say this is a X ton per hour of the steam is produced from this boiler. Then the steam is used in the heat exchanger. Okay. So this is a process stream. Then this becomes to condensate. Okay. So we need to provide the heat. So let's say this is equivalent of the 0.8 megawatt. Then we need heating for the, let's say, 0.7 megawatt. Then during the transportations and the distribution, we might be some loss during distributions and might be some loss in the heat exchanger. Okay, so this thing maybe, let's say, 0.1 megawatt. So the actual heating is done through the 0.7 megawatt. Then the heating initially through the steam is made based on the 0.8 megawatt. Okay, so the 1 megawatt of fuel is used, then 20% is lost during the production of the steam. Then another 10% might be lost during the transportation or distribution or using the heating device. So this is called the efficiency related with distribution. Okay, this efficiency related with boiler. So distribution efficiency should be used, okay? So this is only heating required for the production of the steam. Then we have to consider these 4 elements to calculate the cost of the steam, okay? Then sometimes the steam turbine is used to produce low pressure steam. Like the fuel is burned in the boiler, then the high pressure steam is produced. So HP means high pressure, and the MP means medium pressure, and the LP steam means low pressure, okay? Back to the previous slide. So steam is used, but in different places in your plant, steam is required. But the A plant, we need a 200 degrees C heating. In the B plant, 250 degrees heating. And the C plant, we need a 120 degrees C heating. Okay? And plant P, we need a 160 degrees C heating. Okay? Then for 250 degrees C heating, steam is required at the above 250, so we need high pressure steam. In a plant C, high pressure steam is also used, okay? But the temperature, the gap between the steam of high pressure and the temperature of the plant C process steam is quite big. So we don't need to provide the high pressure steam. Then we can provide the steam, medium pressure steam, or low pressure steam. Okay? For 200 degrees C, we may be able to supply with medium pressure steam. And 160, we may be able to provide the steam with the medium pressure steam rather than high pressure steam. Okay? So based on temperature for the users at the different place, then we can supply different pressure, different steam, okay, at the different pressure. So high pressure steam is used for the high temperature user, and the low pressure steam is used for the low temperature users. Then we have the high pressure steam is produced in the boiler. Then we want to make the medium pressure steam and the low pressure steam. Then, as I said before, reducing the pressure can be either done by the steam turbine or JT valve, okay? So the JT valve is the device to reduce the pressure as well, but this one is just decrease the pressure. But then the turbine is a better device because we can recover the work, okay, power, electricity, by expanding the high pressure steam through the turbine. So pressure is reduced through the turbine, then we can generate work. So the work means is electricity in the process. So the process requires a large amount of the electricity. So rather than buying the electricity from external source, it might be useful to use the electricity or power produced from this turbine, okay? In that case, we needed to take into account the efficiency of turbine in order to calculate cost of the steam, MP and the LP, okay? So HP steam, estimation cost of HP steam is the same, but the estimation of the cost for the MP and the LP steam, we need a turbine efficiency, okay? Here and here. So the HP steam is the expensive one because the HP steam contains the highest enthalpy, highest heating content. But then we are generating power through the turbine. So medium pressure steam is cheaper than the high pressure steam. Then the power is produced from the next turbine. So the LP steam is the cheapest one, okay? So here, generating steam costs are offset by value of the power generated. That is the meaning. This is a quite typical the schematic diagram for the utility system in chemical plant. So there are different places given as process A and process B and process C. Then here process A, process B, process C. There are different the heat exchanger in the process A, several heat exchanger in the B, and several heat exchanger might be processed in the C. Then the process C need a high pressure steam and the medium pressure steam, and the process B we need a low pressure steam, okay, and also the high pressure steam. Then the process A demands low pressure steam. So based on the temperature requirement, we need different pressure levels for the steam. Okay, then so we're producing steam here. That is given by this kind of boiler. Okay, then we are using turbine in order to produce different levels of the pressure. Okay, here high pressure to medium pressure to low pressure. Okay, so the multi-stage steam turbine is used to produce different pressure, high pressure, medium pressure, or low pressure. Then the steam is used. Then sometimes the steam is produced from the side. So then we put the steam back into we call the steam main or steam header for this horizontal line. Then the steam is back to the steam main. Then it is used in some other place. So high pressure steam is produced here. Then that steam might be used in the process B. So there are some the complex interaction between the process within the site. So this is the centralized production of the steam. So steam is produced in one big place and produce the steam through the boiler and distribute through the steam main. So this is called the steam main, okay? These horizontal lines are called the steam main. Then the steam is distributed through this steam main and used in the process. I mentioned that the furnace, okay? This is a furnace. So furnace is used directly for providing heat to the process, okay? So rather than steam is used in the centralized unit, then the furnace might be used as a direct heating. So electricity is produced. So electricity might be used in a driving pump or maybe driving compressor, okay? Then that electricity might be used in the building, in the plant. So the electricity is needed. So rather than just providing the steam directly, it's more economic to produce the electricity, okay, power. Then, if power is not fully produced within the site, then we might need to input, okay, purchase of the power from the external company if the electricity is generated more than enough, then we might selling, okay, the power to the company, external company, okay. So this is a typical the utility system in chemical plant. So we need to understand some thermodynamics related with some power generation. So what we have been looking at the estimation of cost of steam is based on some thermodynamic calculations. So we have to consider some enthalpy calculation and considering the isentropic efficiency explained on this slide. So for example, so high pressure steam, let's say, is expanded to low pressure steam, okay? P2, T2. Then we are generating power, okay? So then we want to estimate how much the power can be generated from this steam turbine, okay? So the initial condition might be given as here. So when we using enthalpy and the entropy diagram, so this is the inlet pressure, okay? Then we want to expand it to the low pressure, P2. So then this is the condition A, okay? Then based on the particular enthalpy, then the steam is expanded. So the expansion of the steam through the turbine means the pressure is reduced, okay? Pressure is reduced to P2. Then this dotted line represents isentropic expansion. So this is ideal expansion through the turbine. Then the entropy is not going to be changed. But the real expansion is not going to be the isentropic expansion. So real expansion probably follow the line. So the rather than H2 prime will be the final condition, okay, for the steam expansions. So the isentropic efficiency is given by that. So in other words, the deviation from the ideal condition that will be taken into account by this efficiency, okay? So based on the particular steam flow rate, then we can estimate the power by using calculating enthalpy from the inlet point to the outlet point. Then because of the non-ideality in the expansion, we have to consider efficiency. That is typically given by so-called isentropic efficiency, okay? Excuse me. The next one is another utility is widely used in the industry. That is the cooling water, okay? So cooling water is used in providing the cold energy to the process, okay? So this is a reactor. Then the reactor is operated at the 200 degrees C. Then this process this process required at 70 degrees C. Then we needed to provide cooling, okay? So cooling is done. So rather than directly pumping from the reactor to separator, then we needed to use the cooling water to reduce the temperature from 200 degrees C to 70 degrees C, okay? So how do you provide the cooling water in the process industry? So this is a common way of the providing the cooling water in the process industry. So the water is supplied, then used in the heat exchanger, then the heat is transferred to cooling water, the hot cooling water returned back to the cooling tower, okay? So the water is needed, then let's say we might have the water tank, then the water is supplied, then used in the heat exchanger. What shall I do this water? So one option is discharge to the environment, okay? So is that going to be sustainable? So this water is a little bit contaminated, so it may not be environmental friendly for directly discharging water to the environment. Then also, if we keep using the water here, then discharging water to the outside, then the amount of water to be used in the process industry is huge. So it's not going to be taken. Of course, this is one method. Okay, this is feasible, but this is not economic. This is not environmental friendly. So rather than the directly discharging water to the environment, then we have the cooling tower, then reduce the temperature, then reuse it, okay? The cooling water. So there are circuit, there are a loop of the water. The water is used, then the temperature here, temperature here. So temperature is increased because the cooling water is taking heat from the process. So the hot return cooling water is cooled down through the cooling tower operation, then they reuse it, okay? So this is called the circulating. Circulating system. So circulating system is quite common in the industry to supply the cooling water and regenerate cooling water, okay? So that's why we have this kind of the recirculating pattern. So water is used in the heat exchanger. Then in the cooling tower, the water temperature is reduced back to the temperature with which we can reuse the water in the heat exchanger in a repeated manner. And the cooling tower is a device to allow the contacting between the air, okay, and water. So the cooling tower, water dropping down, okay. Then the cooling tower, let's say here you might have the influx of the air typically from the bottom. Then heat is transferred from the water to air. So water is gone. Water is recovered in the bottom. The air is taking the heat from the water. So the water is cooled down. So the cooling tower allows this contacting between water and the air. So the temperature here, the temperature is down. Then the water is kept reused inside the circuit. Then if you keep using the water again and again, there might be some buildup of the undesirable material. There might be some contamination in the piping. there might be some the powering in the heat exchanger, then we need some treatment for regulating the quality of the water inside the cooling circuit. So one of the technique is taking out some of the water intentionally from the recirculating circuit. So some of the water is taken out intentionally, then supplemented by so-called makeup water. So the principle for the blowdown is to take out some contaminated water from the system and supplemented with some clean water. So that allow to regulation of the water quality inside the circuit. If you're looking at the operation of the cooling tower, the contacting is the essential mechanism to reduce the temperature of the water. So the air contact with water, then the evaporation is occur, okay? Because of the hot water is losing heat, and the heat is dissipated from the water. So the evaporation from the water is occurred at the same time. So some of the water is lost in the cooling tower operation. So that is also taken into account the supply of the makeup water, okay? So cooling water cost is typically low compared to fuel or electricity. So the buying fuel is expensive, and the buying power from external company is expensive, but cooling water is not that expensive. So the LP steam compared to LP steam, typically the cost of cooling water is typically 5 or 10% of cost. So it's very cheap compared to steam or other utility. So the cost of the cooling water, not expensive. But why is it important? Why is it important to supply the cooling water to the process industry? What happens if you don't have the cooling water? Cooling water itself is not expensive, but the non-provision of the cooling water process industry means we are not having the quality in terms of probably temperature in the process. Then we probably not able to have the proper processing. In this case, separation may be not occur because 70 degrees C should be met through the cooling water. So if cooling water is not supplied, then the 70 degrees C is not made. So let's say 200 degrees C, then separator is not working well, okay? So it's more like the efficiency of the production, or it's more like ensuring feasibility for the production, okay? So the one of common example in the cooling water supply issue is related with the summer operation in our country. In Korea, in the summer, the temperature, ambient temperature is very high. So then the high ambient condition in the plant means the cooling water efficiency is not going to be high, okay? So think about the winter. The winter ambient temperature is low. So in the summer, the ambient temperature is very high. So cooling water is more required than the winter. So in the summer, we needed to provide more water to the process because of the high ambient temperature. So in the big industrial complex in Korea during the summer, it is quite important to secure the supply of the water and the cooling water to the process. Okay, without supply of the cooling water, then we may not have the full production. Okay. In order to understand the cooling water systems, so this is the some simple mass balance to estimate amount of the makeup and the blow down and relationship between these three things, between evaporation and blow down and the makeup. So we need to understand first the concept of the cycles of the concentration, okay, given as Cc. Cc is kind of the operating parameter for regulating the contamination level for cooling water. So Cc is defined as the concentration of the blow down against the concentration of the makeup. So the water is contaminated in the circuit. Then we need to take out some of the blow down. Then clean water will be fed to the recirculating system. So the makeup and the Cm is the indication for the level of the flow rate and the contamination for the water. So as a makeup, the Cm will be very low, okay, because of the clean water. The Cb is high because the Cb represents the contamination level inside the circuit because we're taking out the water from the circuit. So Cb is high contaminant level of the water condition in the circuit. So the relative difference between the two contaminant level, concentration level between the makeup and the blow down is defined as Cc. So I said Cc is kind of the operation variable. So as an engineer, people need to determine the level of the Cc. Some plant high Cc is maintained. The other plant, they might be conservative, so they want to control the water low Cc. Okay, so it's kind of a decision by the engineers. Okay, then if the Cc is defined as Cb over Cm, we can set up the mass balance. Okay, so first mass balance is M makeup equal to B equal to plus E. Okay, so M is equal to B plus E. Then we can have the concentration balance by multiplying the Cm and Cb. So E multiplied with the Ce, that will be the correct form, but the Cv will taken as 0, okay, because the evaporation is probably pure water, so the contamination is not involved in the evaporation, the vapor. So we take Ce is assumed to be 0, then we have this relationship, okay. By solving these two equations together, we have this relationship, okay. So M is given by E Cc divided by Cc minus 1, and B is given by that. So what is the meaning of that equations? Cc is selected. Let's say you take 10, you take maybe 5, okay. So if I'm taking, say, Cc as 5, the meaning of Cc is the relative difference of contamination between circuit and the makeup. So makeup water is given, it's clean water, almost clean water. So then I want to maintain 5 times more contamination inside the circuit. That is the meaning. Once we have that the CC, then we can estimate the M, how much water is required as a blowdown, B, how much water should be withdrawn from the circuit, okay? So we can estimate the blowdown and the, excuse me, the makeup based on your choice of CC, okay? So what about the E? We need to calculate the E. So E is typically a function of the F here and the T2, okay? So this is typically estimated, okay? So how do you estimate? So we might have some rule of thumb. We might have some information from the manufacturer. We might have the reference data from the operation. So this is typically given, or we might rely on rule of thumb. So evaporation is estimated, and CC is the selected or determined or chosen. Then we can estimate M or B, okay? So M was E CC minus 1 CC, and B is E CC minus 1, 1. So I said CC is kind of a decision variable. So what is the consequence of having the high CC? So this is high, this is low. What is the high CC? If the CC number is increased, then the blowdown, okay? Blowdown is going to be decreased, okay? From that equation, okay? Then the maker water will be reduced, okay? So should I keep the big number on the cycles of concentration? Is that economic? Because the maker water is reduced, so we can save the cost on the water in terms of the maker. Is that right? So that is the one aspect related with the concentration of the cycles of concentration. High CC means we can reduce the water requirement for the process, okay? Then the high CC means the contamination in the water circuit is high. So in other words, water is very dirty. So compared to low CC, the high CC range, we needed to increase water treatment. Okay, water is kept used inside the system, so we might have the fouling, we might have some contamination, so we might have some corrosion, so we needed some treatment. So circulating the dirty water inside the circuit means we need more attention on the water treatment, okay? So that is the trade-off. So it's a very case specific. So sometimes a high CC is preferred, sometimes low CC is prepared. So there are the optimal number of the CC, okay? So it's a decision variable. The next one is refrigeration. When cooling is needed at say 30 degrees C or 50 degrees C, then we can use the cooling water. But if the cooling is required at minus 20 degrees C, minus 30 degrees C, then we have to use the refrigeration, okay? Sorry. So this is the process stream, okay? Process stream. The process stream should be cooled down. The temperature should be dropped down in the process stream. Then we need to provide this refrigeration cycle. Excuse me. So in condition 1 is fluid is evaporate through the evaporator. Then at the condition 2, the fluid becomes the vapor. Okay. Then the condition 1 is liquid and condition 2 is the vapor. So through this evaporator, so the heat is transferred from this process stream to this refrigerant fluid. So the latent heat of the evaporation is the source for the refrigeration, okay? So the evaporation or latent heat of the fluid from the condition 1 to condition 2 is the essential part for having refrigeration. So after the evaporation, then the vapor is compressed. So we need power to drive this compressor. Then the pressure is increased. So high pressure vapor is condensed, reduced temperature to have the condition 4, where the saturated liquid is produced. So condition 4 is high pressure liquid. Then that is expanded through the valve. Then the low pressure is fluid is generated. Okay. So in the condition 1 is typically a mixture of the vapor and the liquid. Then the liquid is evaporated, and from the evaporation, the process stream, the temperature dropped down from T1 to T2, okay? Sorry, it might be better to take as A and B, not to confuse it with 1 and 2, sorry. So TA must be reduced to TB, okay? Then the temperature 1 and 2 is not going to be changed because typically is done by the evaporation. So but the condition is a mixture of the vapor and liquid turn to the vapor. So at the condition at 2, the vapor is compressed, then turn to very high pressure, the vapor, then it condensed. Then at the condition 4, we have the saturated liquid. So through the valve, then we have the low pressure of the fluid, that is mixture of the liquid and the vapor. Okay, so this part is the main element for the refrigeration. But in order to have the evaporation, we need compression. So compression is needed. This is the main cost for the enabling refrigeration. Okay, so how do you estimate the cost for refrigeration? Then we needed to estimate cost for driving the compressor, and we needed to find out the cost for cooling. So stream condition from 3 to 4 is done by typically by, say, cooling water. So cooling water is used to reduce the temperature from condition 3 and condition 4. So we need two elements in terms of the estimating cost for refrigeration. One is cooling water, the other one is electricity, okay, power. But compared to power, cooling water is very cheap. So we are only considering power cost, okay, for estimating the refrigeration cost. So here I'm introducing so-called coefficient of the performance known as COP. That is the relative difference between the heat to be discharged to the refrigeration against power required by compressor. The power required by compressor is given by W, and the heat to be transferred to refrigeration cycle is given by QC. So QC is cooling duty. Okay, cooling duty by the refrigeration is given by QC. Then the W is given by power. So the COP means in order to achieve the cooling in the evaporator, then to estimate the power requirement for this process refrigeration cycle. Then the high COP means low power requirement. So that is good for the cycle. If COP is low, so the power is high. So power requirement is high. So the cycle is not effective. Okay, that is the indication how we use the COP for comparing different refrigeration cycles. So COP is kind of a measure of the energy efficiency. So how do you estimate the cost further? Then we first look at the ideal COP. Ideal COP means the condition is given by without considering any the element of the inefficiency. Okay. So ideal COP is given by QC of the W. So W is the power requirement. So the subscript ideal means is that the ideal power requirement. But the actual power requirement should be based on the efficiency. Okay, so that is taken as the efficiency value. So this is the equations. Once we have the COP, then we can estimate power requirement. So QC is cooling duty that is typically given. Okay, so based on the QC, we can estimate this power requirement using COP. Thermodynamically, this is the equations we can use. How do you get this equation? I'm not going to discuss how we get this expression. If you are having thermodynamic books, then you can find this relationship from that book. Okay, so I recommend you to look at that section, how we can get this expression. That is more like a thermodynamic subject, so I'm not going to cover from this one, but you can, it's not that difficult, so you can look up the book and see how we get this expression. So what is the TEVAP, evaporation? So the T evaporation is the temperature in terms of the absolute, is the temperature where heat is taken into the refrigeration cycle, okay? So that temperature, okay, that is the T evaporation, okay? So what is the condensation temperature? In terms of the absolute term, the temperature where heat is rejected from the refrigeration cycle. So heat is rejected from condition 3 to condition 4. So this temperature, okay, this temperature is T condensation. So in a refrigeration cycle, there are two major thermodynamic temperature. One is condensation temperature, one is evaporation temperature, okay? So based on this temperature, we can estimate the power requirement, and cooling duty is typically given. Then once we have this ideal power, then using the efficiency, then we can estimate the actual power. Once we have the actual power, then you probably have the cost, unit power cost, okay? You have the unit power cost, then based on the unit power cost multiplied with the actual power requirement of the refrigeration cycle, then you can estimate the cost for the refrigeration, okay? This table shows some the typical the range of the cost for the utility. So this is not the only one reference you can refer. So there are other suggestions, other guidelines in terms of the utility cost. But I'm showing one of the examples as an illustration. So different utility are used. So I explain the key utility are used in the industry today. So the refrigeration and the cooling water and the steam. But there are some additional the utility like air supply, for example, then and waste disposal. So there are some other elements related with the utility cost. So this is for your some supplementary the material for better understanding in your study, okay? So if you look up the different books or different journal or different reference, you might have a different cost range. So of course, the cost of utility is very case specific, it's very region specific, it's very industry specific. So if you work in the company future, you have to bear in mind that the estimation of utility is very complex. So you can use this number from the book or journal or other database, but you should be very, very careful because it is very case specific, okay? Before going to the working sessions, okay, I don't have space, okay. I'm going to explain some the very important issue the related with the utility cost. We have the refrigeration, we have the cooling water, we have the steam. So this is the cost. Let's say this is the temperature. Then when temperature of the utility is increased, then the cost is going to be increased, okay? So high pressure steam is expensive, more expensive than the medium pressure steam. And the medium pressure steam is expensive compared to low pressure steam, okay? What about the cooling water? Cooling water is the cheapest one. What about the refrigerations? Refrigeration is opposite. So cooling at the -20, cooling at the -50, so cost is expensive. Cooling at the -70, -100, okay? The lower, the more in terms of the cost, okay? So we have this kind of a trend or profile for the cost. So the 250 degrees C cost is 150 degrees C hot utility. So 250 is expensive, okay? 350 expensive, okay? Up, okay? So when the temperature is increased, the cost of utility cost is increased significantly. Below the cooling water for the range of the refrigerations, then the low, the cost is increased significantly. So you needed to aware of this relationship, okay? One more thing I needed to discuss from this section is the air cooling against the cooling water. So at the ambient cooling, we can use cooling water, but we can use air. Okay, so which one is better? That is my questions. Okay, cooling water is better or air cooling is better? When you're back to the steam, the first major advantage of steam used in the process industry given as steam has a high heat of condensation, so low flow rate is required. Okay, that was the advantage for using steam. So same principle can be applied. The cooling water and compared to air, heat capacity is better for the cooling water than the air. So the flow rate, cooling water, flow rate of the air is different. So we need a large amount of the flow rate in order to provide cooling through the air. So let's say if we want to have the 1 megawatt of the cooling, then the flow rate of the cooling water, flow rate of the air required to provide 1 megawatt is different. So the more flow rate, larger flow rate, bigger flow rate mean then the piping should be increased and the heat exchanger, okay, is to be bigger because of the large flow rate, okay? So the cooling water is more effective than the air cooling, okay? So this is the first reason. There are another reason, okay? There are another reason that is based on the thermodynamics reason. So let's say the ambient temperature is 15. So the ambient temperature 15 means air temperature is, you can take the air temperature is 15, okay? So that is basically meaning of ambient temperature. Then the lowest temperature you can service for the cooling is 15 degrees C plus alpha, because the process stream to be cooled down is the higher than the 15 degrees C. Let's say 50 degrees C, maybe 25 degrees C. Then we use the air. Then that is supply at 15, okay? So this is a process stream to be cooled down. What about the cooling water? So the ambient temperature is known as dry bulb temperature, okay? Cooling water is typically governed by wet bulb temperature. So the cooling water temperature is lower than the 15 degrees C because wet bulb temperature is lower than dry bulb temperature. Maybe 3 degrees C, maybe 5 degrees C, okay? So the cooling water temperature, supply temperature is lower than the 15, okay? So we can supply the water at the lower temperature compared to air temperature. So in terms of the taking out heat from the process, provision at the lower temperature is better. So because of these two reasons, cooling water is better than the air, okay? But then question is why we needed to use air rather than the water. So in some case, air is used. We need a source for the water in terms of the using cooling water. Otherwise we have to use some other cooling source. So in our country, in Korea, the supply of water is not the big issue. But if you want to supply the water in a desert, if you want to supply the water in the certain country, in the Middle East, for example, then it might not be easy to secure the water supply. In that case, we do not have the option for using the air for the cooling. Okay. Now, when you design the system, the plant using cooling water, you should bear in mind of the geographical difference. So if you want to use the cooling water in the Alaska, if you want to use the cooling water in the Middle East, if you want to use the cooling water in Korea, that is different, okay? Because that is regulated by the ambient temperature. So in the Alaska, that temperature might be, say, maybe 2 degrees C. In the Middle East, it might be 30 degrees C. In Korea, is maybe 15 degrees C. In the winter, maybe in the fall, in the summer, it might be 25 degrees C, okay? So it's a geographic specific number. You should be very careful in terms of the selecting the source of the water and the use of the water and for the cooling, okay?